Okay, good morning everyone. Welcome to this seminar, and I'm very pleased to introduce speaker Roshan Dathathri, who is an alumnus from my lab. He did his master's here at IISc, graduated around 2013, and subsequently could convince him to do a PhD. So he went to UT Austin for his PhD, where he worked with Keshav Pingali, and is basically close to submitting his dissertation. He's done some outstanding work again at the intersection of domain-specific programming languages, compilers, and runtime systems. He's done an internship at Microsoft Research at Seattle Arithmetic, right? And basically, and some of the work that he's going to talk about is also in collaboration with them. This is built programming systems for distributed and heterogeneous graph analytics. This PhD work at UT Austin, and privacy preserving neural network inferencing is also something he has worked on. And so we are very pleased to have him. He also happens to be the first lab alumni brave enough to come back and give a talk. And no one else has so far come back, although a lot of them are doing interesting work. And so it's very nice to see doing some excellent work. And he's also interested in coming back to the academia as a faculty member. So trying to convince him to again come to IISc. So this talk that he's giving is on an optimizing compiler for Fully-Homomorphic neural network inferencing, and it's done in collaboration with both folks at Microsoft Research and I guess UT Austin also. Right? So, just Roshan from UT Austin, so it's mostly his internship. Okay, so look forward to it.
Thank you. Good morning, everyone. Today I'll present work that I did primarily during my internship at Microsoft Research last summer. This was accepted into PLDI this year. So there's a lot of sensitive data like medical or financial data with hospitals and banks, and there are many applications which would like to analyze this data. One such application is, say, during neural network inference on such sensitive data. One way to do such computation without violating the privacy of such data is to use fully homomorphic encryption, or FHE in short. FHE allows computations on the encrypted data directly, so the users can offload both their storage as well as the computation to the cloud without revealing the privacy. The computational overhead of FHE has been rapidly decreasing over the years, and it's within reasonable bounds now. Moreover, the trust model is very simple. So as long as the client or the user keeps the secret key, there is no need to trust the hardware or the software vendors like Intel or Microsoft. So this is known as a semi-honest threat model. Moreover, this is quite secure, it's post-quantum safe, and it's even immune to side channel attacks. However, the challenge in FHE is that programming FHE applications is very hard. So it requires cryptographic domain expertise, and it is similar to writing low-level assembly programs for custom hardware. So in this work, we develop a compiler called CHET to address these issues, specifically for neural network inference. So in addition to addressing these issues and making it easier to program, CHET also generates programs that is very efficient. So here,
why do you call it post-quantum safe?
So in terms of the term or is
You use the word. I want to know what.
Okay. So it just means that the encryption scheme could also be secure in the case of quantum computers. So
No, but it's standard encryption is not quantum safe.
yes. But this scheme is dependent on what is known as learning with errors. The fully homomorphic encryption schemes, they use learning with errors property, and the learning with errors is safe even in the presence of quantum computers. So it's hard even for quantum computers to do. Does that make sense? Yeah, okay. So it also generates very efficient programs. So here are 5 different deep neural networks, and I'm showing you the latency of inferencing these networks using CHET. And this is all in the order of a few minutes. Specifically, for the largest network, SqueezeNet is the largest deep neural network that has been homomorphically evaluated, and we were the first ones to do so. And for another network, which is a medium-sized MNIST network, so a naively written FHE code used to take around 900 seconds. In a month or so, cryptographic experts were able to write efficient code and reduce it to around 140 seconds. So when I started my internship, this was the target to beat. Within a month or so, we were able to incorporate all the cryptographic expertise into the compiler and automate it so that we were able to match the time to 130 seconds. And over the next few months, we added several optimizations and moved to a more advanced FHE scheme, and we were able to reduce it to just around 11 seconds. So it's an order of magnitude faster than even expert written code.
Just a quick question. So here, when you say data is encrypted, it's the weights of the neural network or weights and input?
It's just the input. So what we are getting, so the weights are not encrypted. So only the data is encrypted. So in the sense that the image or the user data is encrypted. So you want to say predict based on the credit report or whatever of the say customer. So that is encrypted. The model itself is not encrypted.
Okay, and this got faster and faster. The expert tuned code didn't get faster.
No, this is the manually written code. All this line is saying is what was the target that we had to beat. So this 140 was the target that the compiler had to beat, and different versions of the compiler over time by adding more optimizations we were able to do faster.
Oh, I see. But it looks like a huge, like almost 14x speed up.
Yeah.
But the expert tuned code stayed at 922 seconds or 140 seconds.
Yeah, this is the manually written code. Yeah, it's very difficult to optimize it further. I mean, we didn't spend time because the compiler were doing it fast. So, for example, I'll show you a couple of compiler optimizations, which if you have to do it manually and write code for it, it's just just like how if you have to write the manually tuned tiled code, it's very difficult. It's the same.
Suppose you don't use homomorphic, you actually decrypt it. What is the time? So milliseconds, what is it?
So even with this optimized code, the overhead. So when I say the overhead of doing encrypted computation versus doing unencrypted computation, even right now it's 2 to 3 orders of magnitude. So we are 2 to 3 orders of magnitude slower than unencrypted computation. So first, let me introduce more formally what fully homomorphic encryption is. So consider two plain text messages A and B, which are then encrypted to provide two ciphertext messages corresponding to it. This encryption scheme is said to be homomorphic with respect to an operator, say addition. If there exists an operator on the encrypted ciphertext whose result when decrypted is equal to the addition of the two plain text messages. So in this case, this encryption scheme is homomorphic with respect to addition. So fully homomorphic encryption, or FHE in short, are schemes which provide homomorphic operators for both addition and multiplication. So conceptually, if the operation is in binary, they can handle arbitrary computation. For example, the popular RSA scheme is homomorphic with respect to multiplication, but not with respect to addition. So the homomorphic schemes that we see here, which we use FHE in short, provide homomorphic operators for both addition and multiplication. So when FHE was first introduced by Gentry in 2009, it was the encrypted computation was 12 orders of magnitude slower than unencrypted computation. So it was not at all feasible. But in the last decades or so, due to advancement in both theory and implementation, the overhead is around 3 to 4 orders of magnitude. So it's reduced drastically. And most of these is because of theoretical implementation, theoretical innovations, which also make it difficult to program. And some of it is also because of implementation. So right now, most of the implementations just use CPU, but there is work in progress to use GPUs, FPGAs as well to reduce this overhead. And I believe this overhead can be reduced further by building better compilers and systems. And to demonstrate this, we take the neural network inference app and show that this can be done. Any questions on this? So right now, the 3 to 4 orders of magnitude, if you see the performance of computation, it's similar to that of an 8086 processor a few decades ago. So that is still quite slow, but it is sufficient to do some useful computation, like neural network inference.
So going forward, you see, because you increase by a factor of one order of magnitude, right? From 140 seconds to 11 seconds.
Yes.
How much more down can it go? What is your expectation?
So I think we can get at least 1 order of magnitude more quite easily, even without exploiting additional architectures. But the goal is like this, at least the goal from the sense of Microsoft is this. Even if the overhead is not reduced further, we can deploy more hardware to do that. So for example, we can deploy FPGAs, and that is an order of magnitude in itself. and we can deploy distributed FPGAs and so on. That will give you more. So we are not comparing hardware apples to apples. We are not comparing a CPU with another CPU. There maybe we can do one more order of magnitude without theoretical advances. There could be more theoretical advances. Okay. So one such app is the neural network inference app. So to demonstrate what we mean by using privacy-preserving neural network inference, so consider an image whose digit you want to recognize. So the user does not want to reveal the contents of the image. So the user encrypts the image and then sends it to the server. So this is the privacy barrier. The server computes, performs the neural network inference on the encrypted data directly, and then sends the encrypted result back to the user. So the user then gets an array of 10 numbers, they're decrypted, and the index of the maximum number in this array corresponds to the digit in the image. So the index is 2 here, so the digit is 2. So in this way, the server performs the computation on the encrypted data. It's not privy to the input image, to the output prediction, or any intermediate state in between. So this is preserving the privacy of the user's data. However, the challenge here is in actually expressing this computation. So there's some delay in the okay. The challenge here is in expressing the neural network inference on this encrypted data. So earlier programmers used to write these FHE applications directly for 1 or 2 FHE libraries, which used to run on CPUs. So in this work, we raise the programming abstraction. So the user specifies programs in terms of tensor programs, so something similar to what is there in TensorFlow. And then our compiler, CHET, compiles it to run on FHE libraries, which then run on CPU or GPU or FPGA. In the future, they could even run on the GPU or FPGA. So currently, we support 2 state-of-the-art FHE libraries. They support integer or fixed point arithmetic, and currently they have been implemented for CPUs, but in the future, they themselves can be implemented on other hardware. We have a runtime which provides a library of optimized tensor kernel. So this is similar to Intel MKL library for linear algebra operations. So the runtime itself provides optimized implementations for certain high-level operations, and then the compiler generates or targets this runtime from the high-level tensor program. So it automates all the error-prone tasks, and it includes optimizations to improve the performance. Any questions so far? So in the rest of the talk, I'll focus on 3 different things, 3 different optimizations, but some of them are also needed to execute the code. So the first is how to ensure that the code that is generated is correct, secure, and performant. So in typical compiler optimization, you just need to ensure that it's correct and performant. Here, there is a third parameter that needs to be obeyed, which is the security. And then I'll show you how we can map high-level tensor operations like matrix multiplication or convolution onto the limited instruction set that is supported by these FHE schemes. Finally, I'll show you an FHE scheme-specific optimization. So all these optimizations are specific or target dependent. They're specific to the FHE scheme. So we support only 2 FHE schemes, which are fixed point FHE schemes, Yon and C. But in general, we can extend these for other architectures or other FHE schemes as well. So in our perspective, in the previous slide, what I should have made clear is that from our perspective, our architecture or the target is an FHE scheme. So that is what we are targeting. That itself, instead of a library, we see it as a new architecture.
So since your focus is on inference, I think integer fixed point arithmetic makes sense. That's what people use.
Yeah. So I'll recommend you to read the paper for other optimizations or the more subtleties involved. Okay. So the first thing is when we encrypt. So in these FHE, so in the rest of this talk, when I say FHE, I just mean Yon and C. So in FHE schemes, the ciphertexts are represented as polynomials with 2 different parameters. So the 2 parameters are the degree of the polynomial n. So it is the largest power, and then q, which is the modulus of each coefficient in this polynomial. So each coefficient here, if it grows beyond q, then the value is lost. There's no way to distinguish between a value which is not over the q and a value which is actually over q. So in some sense, for a given program, so there's a minimum value of q for which the program is correct. So if the value of q is smaller than that, then the program would be incorrect. And this actually depends on the program. So if you make minor changes to the program, the value of q for which the program is correct might change. Right? And then for a given value of q, there's a minimum value of n for which the program is secure. And this is determined by the FHE standard or the FHE experts. So the larger the value of q, larger the value of n that is required to make sure that the program is secure. So when I say secure, it's typically they have different security levels. So a level is, say, if it's a 128-bit level, it means that 2 power 128 number of operations is required to crack it or to get to know the data. So here I've approximated them as straight lines, but in general they're not straight lines. It's just for abstraction. So there is, for a given program, there are certain values of q and n for which the program is both correct and secure. However, larger the value of q and larger the value of n, larger the size of each ciphertext and larger the cost of each operation, encrypted operation, multiplication or addition. So in general, smaller values of q and n are better. And depending on the program, depending on changes to the program, this keeps changing. Doing all of this manually is highly error prone. So typically programmers just choose a very high value conservative. What CHET does is it chooses these n and q automatically and chooses it such that the code is also performant. So to show how it does it, let me just take an example. So here, as I said, Heon and Seal support approximate fixed point arithmetic. So what I mean by that is they take two real numbers and encode them as integers with a fixed scaling factor. So here 1.1 and 2.2 are encoded as 11 and 22 with a scaling factor of 10 each. Then they are encrypted, and if you want to do a multiplication of that, then the encrypted message now has a scaling factor of the multiplication of the two scaling factor, 100. So if you keep doing encrypted multiplications like this, the scaling factor grows exponentially with the depth of the multiplicative circuit. Right? So to overcome this, an innovation in these FHE schemes, Heon and C, is that they support an operation known as rescaling. So this rescaling operation divides the encrypted message as well as the scaling factor by the same integer. So here the integer is 10. And then after decrypting and decoding it, the value is 2.4, which is approximately equal to the multiplication of the two fixed point numbers. So there is some approximation involved. There's actually another layer of approximation, but I'll not go into that. So this rescaling operation also consumes the modulus q. So the modulus q is also divided by the same integer which is being used in rescale. So the rescale operation divides the modulus, it divides the encrypted message, it also divides the scaling factor. Using this information, we can then use analysis to determine what is the q that is required for the circuit. Okay. So we can do data flow analysis. So if you have a circuit like this with rescale operations, so the rescale operations consume the modulus. How the modulus is consumed depends on the scheme. So what I showed you was for the Heon scheme. For Seal, it is slightly different, but the details are not important.
If you keep scaling the modulus also, it becomes smaller and smaller and smaller.
Yeah.
And it becomes almost 0. I don't understand this part.
Okay. So if you scheme, the point is if it becomes less than 0, the value is it's incorrect value. That's the whole point. So you need to have a q, which means that it will not decrease throughout the circuit.
So you start with a large q.
Yes.
But in spite of the number of depth of the multiplication, whatever it is, you still have reasonable qs.
Yes. So to put it another way, so the q depends on the depth of the circuit, right? So for a given program, there's a minimum q for which it is correct. So the encryption that you choose only supports some amount of computation up to a certain depth. That is the innovation in this.
Why do you have to scale the modulus? What is this? It's not clear.
That is the FHE scheme. That's the way it is. Why do you have to? Sorry, repeat the question.
Scale the q. Q went from q to q by 10.
Yeah.
What is is there an intuitive explanation for it?
No. So the rescale operation itself. So this is this is cryptographic. So the rescale operation, to actually rescale the scaling factor, so actually divide these two, they also have to consume the modulus. It's a part of the cryptographic thing. And the reason they do this is because otherwise you need a much larger queue than. So now what I didn't say, sorry, I missed that, is Because of the rescaling operation, the Q that is required is linear to the depth of the circuit instead of being exponential to the depth of the circuit. And that is one of the reasons why we can actually do efficient computation. Because if you have a very high depth circuit of multiplications, earlier you needed a very large Q, which means you needed a very large N and everything was much slower. Because of this rescale operation, it goes linearly now, which means you can do much larger depth circuits.
Excuse me. So what about neural networks that have feedback like
Right now we are not considering. These are only CNNs, convolutional neural networks. So to determine the Q, you need to determine it so that you have some valid Q in the end, which is exactly what the data flow analysis does. You determine how much Q is consumed. I mean, each rescale operations consumes some Q. The rest of the operations just propagate whatever it is there. So at the end, we know how much Q will be consumed by the entire circuit. So we can set the initial Q to be larger than the minimum required thing so that you would get the correct answer. And given this Q, you can determine N, which is basically a table which is given by experts. So you can determine the minimum Q and N for which the program is both correct and secure. So that ensures that the program is both correct, secure, and performant. So next challenge or innovation in FHE is that, so even rescaling is an innovation which made more programs feasible, but it was more difficult to handle. The other innovation, which is slightly older, is what is known as packing or patching. So what I showed you earlier is there was a single message and I was encrypting it into a single ciphertext. But in practice, FHE schemes allow packing many plain text messages or scalars into a single ciphertext vector. So, but the size of the vector is fixed and it is fixed to n by 2. So n is at least 2 part n, and in practice it is actually much larger for largest programs. So the vector width is very large, it's thousands of elements. So if you want to encrypt the 6 elements and if the vector width is 8, you can pack them into the first 6 elements and the last 2 you can just put zeros. So, and the FHE schemes support operations on these vectors, but there are limited set of operations. You can do element-wise addition, subtraction, multiplication, rescaling, and rotation. So for example, you can multiply all the elements of these with 2, and if you have a 0 there, that would still be 0. However, random access of a vector is not supported by the FHE scheme directly. So to access, say, an element, say if I want to access 132, I can rotate it so that it comes to the first position, and then I can mask everything else. The mask basically keeps 1 here and multiplies everything else with 0. So that is the mask, and then I can get this ciphertext with just that value. However, both rotation and masking are very complicated or very expensive operations, so it's not recommended to use this regularly. So the challenge is in actually mapping high-level operations like.
Oh, sorry, you finish. You can just.
Yeah, so the challenge is mapping high-level operations onto this limited instruction set and limited instruction vector instruction set. So these are not, in some sense, they are similar to SIMD processing units, but it's much more restricted in the sense that you can't access a random element. There's no scatter and gather supported.
So again, I'm confused here. So this is just standard SIMD operations on FHE data. So why is this? Is there separate hardware?
No. So when I say hardware, I'm just talking about FHE scheme. So again, similar to the answer, this is the cryptographic. The way they do it in cryptographic is you can only do. So all operations that you do are on polynomial. So each of these, I'm representing the ciphertext as a vector here, but that's the abstract representation. It's a polynomial, and there is an equivalent operation on the polynomial, which is equivalent to element-wise addition on this vector, or element-wise multiplication on this vector, or rotation on this vector. But there is no, get me the random access element. There's no equivalent operation for that on the polynomial. Does it make sense?
Yeah. So basically, if I'm packing more data, does the degree of the polynomial also increase proportionally, or it remains fixed?
So the degree of the polynomial is chosen first. So given a degree of the polynomial n, the vector width is fixed to be n by 2.
So
you can, if you want, if you want to pack more elements, you can go to a larger n, but that's typically not recommended because every operation size will increase. So if you have some operations which are not utilizing the entire n by 2, you are paying much higher cost.
Okay.
right?
Because of this vectorization now, because once you define n, the cost of the operations are fixed.
Yes.
Now with vectorization, basically you are able to do more with the same amount of computation.
Exactly. You're trying to amortize the cost of each operation. It's basically you're trying to utilize the vector bit so that you're amortizing the cost.
That also means that you need to increase the batch size accordingly.
The max?
The batch size accordingly. So, because now you are packing multiple executions together, you're basically increasing the batch size.
So that's a good question. So one thing you can say is, right, so a simple way to actually utilize this entire bit is just to increase the batch size in the neural network size. So instead of doing inference for one image, you can do inference for thousands of images simultaneously, right? So that is easier to do, but that's not what we are looking at here. So here we are looking at inference for a single image at a time. And there's a reason we are motivated by this. So if, say for example, there's a health data, your health data, so there's some scans of you. The private key for your data might be different than that from some other data. You don't want to batch everything and encrypt it, right? So that's the reason we want to support image inference of a single image. You're not using batching at the higher level.
Yeah. Basically, batch size 1 is what we
Yes, batch size 1 is what we are doing. Doing batch size larger than that is not that difficult, which is what there's another scheme which has come after us, which is known as ngraph. That's what they do. And that's actually quite simple to do. I mean, you can easily utilize the entire vector. You just increase the batch size up to that. Oh, sorry. Okay, so now the challenge is in actually mapping high-level operations, like say matrix multiplication, into this low-level instruction set. So let's say that you want to do multiplication of A cross B, and A and B are 2 cross 2 matrices here. So a simple way or a naive way to do matrix multiplication is to encrypt each element into a separate ciphertext and do matrix multiplication the traditional way. This would be 2 cube number of ciphertext multiplications, which is 8 matrix multiplications. This is very expensive, and if you have a very large matrix of size n cube multiplications would be very, very expensive. So instead, what we can do is we can pack the elements of A and B into 2 different ciphertexts. So here I'm laying them out into 2 different ciphertexts. So both of them are in row major order, but notice that they are packed in slightly different ways. So for B, all the elements are contiguous. Excuse me. But for A, there is a gap of an element. There's a padding of 0 in between. And there's a reason to do this. So for B, once I have it in this layout, I can rotate them by 4 and add it up. Now the elements of B are duplicated, but I'm utilizing the entire vector. For A, I can do something similar. I'll rotate by 1 and add it up. So now the elements of A are also duplicated, but the duplication pattern between A and B are different. And the reason to do this is now if I have the vectors in this form, I can do a single ciphertext multiplication to get all the partial sums that is required to compute C. So I have all the partial sums that I need, and then I can rotate and add those partial sums to get the actual elements of C. Of course, there are some elements here which are garbage, and I can remove those garbage elements by masking it out. So just by doing 2 ciphertext multiplications as opposed to A, I have the output vector C. So there are 2 things here. This can be done for very large matrix sizes n as well, as long as the vector width is large enough. So instead of doing n cube multiplications, you may be able to do just 2. Even if your vector is not large enough, you can do much fewer number of multiplications. The other thing to notice here is the padding here of the output C is different from that of the input. So if you have a sequence of matrix multiplications like this, it becomes very hairy to manage all of this automatically. And this is what CHET does. So CHET selects these data layouts and handles all of these transparently. And it does it by both using a compiler and the runtime. So the runtime will manage all this padding. However, there are many ways to map the high-level tensors into a single ciphertext or a sequence of ciphertext. Here, what I showed you was a 2-dimensional tensor, which is a matrix. So you can pack all of it into the same image. So consider a 3-dimensional tensor instead, where we have a channel dimension, height and width dimension. There are many ways to map a single such 3-dimensional tensor into some vector, a vector of vectors. Right? And there are different trade-offs with these. And the compiler selects which is the best way to go about it and chooses the trade-off efficiently. So let me just show you 2 different layouts, and this is what we support in our implementation. So the first layout is known as the height and width layout. So in this layout, each channel is in a separate ciphertext. So there are 4 channels here, so there are 4 ciphertexts correspond, 1 per channel. So the advantage with this is that convolutions on this ciphertext is easy because all the channels are aligned and you don't need to do any rotations. The disadvantage is that the vector width might not be utilized well, so there might be a lot of wasted space. So another layout is known as the channel height width layout. Here, it is allowed to put more than one channel into a single ciphertext. Of course, you might not be able to fit all the ciphertext, all the channels into the same ciphertext. So you will get better space utilization, so the vector is utilized more efficiently. However, convolutions now become more complicated because you need to rotate one to this position to actually add them up. So like in terms of operations, you might need more operations. So to choose the data layout automatically, we first need to define the search space, which is explore all the possible data layouts. And then for each point in the search space, we need to estimate the cost. And then we just pick the best performing one. So the search space is exponential in terms of the size of the circuit, not the depth of the circuit. So for each operation in the circuit, the output, even if you say there are just 2 operations, which is what we support currently, so the number of if the number of operations is n, then there are 2 power n options, or the size search space is 2 power n. So we prune this search space by using domain knowledge and limit it to only 4 choices. The domain knowledge is quite simple. So for each of these high-level operations like convolution, we see which layout is better. So for example, in convolution, it is always faster in the HW layout if both the inputs and outputs are in the HW layout. Whereas for all the other operations, they are faster in CHW layout if both the inputs and outputs are in that layout. For matrix multiplication, the output is faster if it is faster if the output is in CHW, even if the inputs are in HW. It's okay to translate in between while doing the operation. So using this, we have restricted the search space to calculate the cost of each of these. We build a cost model for the FHE primitives. So what is the cost for a ciphertext multiplication? What is the cost for ciphertext rotation, and so on. To do this, we know the asymptotic complexity from the FHE experts, and we use some micro benchmarking to determine the constants there. And the cost of a circuit is just the sum of the cost of all operations, and then we can pick the best performing one. So in this way, we have systematically explored different ways to lay out high-level operations into these low-level instructions. And this is very tricky to do manually by a programmer. We do all of this automatically and choose the best performing one. So the other optimization is specific to an FHE. So what I didn't get into earlier is I said that the secret key need not be revealed. But there is a public key, so there is a public-private cryptography. So that there's a public key to do computation. So to do other computation, there's a single public key, but to do a rotation, you need a different public key for each distant rotation. So if you have to do it by rotation by 3 and 5, you need 2 different public keys. And each public key consumes significant amount of memory. So to trade off memory, what FHE schemes currently do support is that they generate power of 2 rotations. And they do all rotations using this. So if you have to rotate by 5, you would rotate by 4 and then by 1. So this increases the number of rotations, but it decreases the number of keys that you may need. This is very conservative. Even though the number of keys are just log n, you might be doing many more operations than are needed. So what we instead do is we use a compiler analysis for a given program. We calculate all the distant number of rotations. And in general, given these distant number of rotations, you can find the minimum number of keys in some constraints and so on. But in practice, we notice that the distant number of rotations for all these programs are not that high. They are of the order of log n. So we simply generate rotation keys for all of them and use them directly. So to evaluate, we take manually written Qion code. So this is written by experts. For example, the one that I showed you earlier for one of the networks. And then for the same library, we generate CHET code and we show how much performance we can gain by that. And then for a newer library, which uses a more advanced scheme the library is called C. This is much more difficult to program. In fact, even for small programs, it's very difficult to write because the way it does rescaling and so on is much more complicated than what I showed you there. So this was actually done so that because we have compiler CList from Microsoft, this was implemented because now we have compiler support, we'll be able to do better there. And using that, I'll show you how we can do much faster. So the system that we evaluate is on 16-core dual socket machine with 224 GB of memory. So we evaluate 5 different deep neural networks. So the first 3 are for the MNIST dataset. The last one, SqueezeNet, is for the CPAR10 dataset. There's also a network from our industrial partner. This is on medical data, and it's a classification data. It's a binary classification data. And there are many different layers. The deepest one is SqueezeNet, and millions of floating point operations. So the accuracy that is shown here is that of unencrypted computation. So all these layer networks have been modified because since we are doing integer or fixed point arithmetic. Say, for example, if you want to do ReLUs, that is not supported by FHE at all. So we have modified ReLUs to polynomial activations. We have modified max pooling to average pooling, and so on. So with these modifications on unencrypted computation, this is the accuracy that is achieved. And encrypted computation also achieves similar accuracy. So we evaluate, as I said, using latency of image inference, which is just a single batch size equal to 1. So first, let me just show you the average latency. So on the x-axis, I'm showing you 5 different networks, and I'm showing you 3 different things: manually written Beyond code, as well as state-generated code for C and Beyond. On the y-axis, I'm showing you the average latency in log scale. So the blue line is for manually written codes. So notice that, first of all, for the large networks, the NetFile Lab and SqueezeNet, we don't even have manually written code for Beyond, because once it becomes that large, it's very difficult to keep track of what is needed, where to insert rescaling, and so on. And the orange line shows using the same library. So we are using the same architecture, and everything is the same. It's just that what can the compiler do? And even with that, you can see that we are much faster than the manually written code, because we have data layout optimizations and rotation optimizations and so on. So it's it's around 4x faster, roughly 4x faster. And once you move to a different, more complicated, more difficult to use C, we get another 2x to 3x improvement, and that's the red line. So overall, we are on average an order of magnitude faster. And for larger schemes, it's not even feasible to write these codes manually. So see where these improvements are coming from. So first, I'll show you the 2 different optimizations and how what is the impact of these. So first, there is the data layout optimizations. So on the left side, I'm showing you for C, and on the right side, I'm showing you for CAM. So all these are compiler-generated codes. On the x-axis are the different networks, and the different bars correspond to different data layouts. You don't need to look at the labels and see what they represent. There are just 4 different data layouts. Right? And these are the 4 pruned data layouts for the entire circuit that I told you about. So on the y-axis, I'm showing you the slowdown of these codes compared to the best performing data layout for that scheme and network. So if you see, which means lower is better. So if you see, for the same network, given the different FHE schemes or hardware in our perspective, the best performing data layout could be different. For the same library, for different networks, the best performing layout could be different. So doing this manually or keeping track of this is not feasible. So, and in all of these cases, CHET chooses the best performing data layout automatically. To show something stronger, what I'm showing you here is on the x-axis, I'm showing you the estimated cost. On the y-axis, I'm showing you the average latency for all those points. You don't need them to be, you don't need x equal to y line here, because that's not what we just want to be able to differentiate between this. So a single line like this, it says that higher the cost, it means that the latency is roughly higher. So CHET is, our cost model is sufficient to actually differentiate between the different points, and we do select the best performing one. So finally, I'm showing you the impact of choosing the rotation keys automatically. And here on we are getting up to 2x speed up, and on average we get around 1.5x speed up. And it again depends on the scheme. So there have been several different compilers for deep learning. So there are several optimizing compilers like Halide, TVM, tensor comprehensions, and so on. In our perspective, FHE is just another backend. Instead of targeting, say, a new heterogeneous architecture, you just target FHE. Instead of providing performance, it gives you security. That's the key difference. For FHE, we are the first optimizing compiler for deep learning. We have just scratched the surface. For example, right now, all we are doing is automatic layout selection. There are many other things that can be done, which are being done by current deep learning compilers, like scheduling language, automatic tuning, automatic kernel generation, and so on. So there are a lot more optimizations that we can explore in the future.
Sorry, have you tried plugging in, using any of these infrastructure to plug in your?
No, not yet. So the plan actually, okay, this is internal, but it's not yet confirmed. So what we actually want right now, when I said tensor programs, we use our own interface. With engineering effort, it should be simple enough to say take Onyx or TensorFlow and so on. That is what we are looking at next. And once we have it, say, then we can use that infrastructure to take and do additional optimizations. It could be MLIR, it could be DBM. So to conclude, I hope I've convinced you that FHE compile programming is a systems and compiler program, and where we can do much better and show greater performance. CHET outperforms handwritten FHE implementations by an order of magnitude. It enables larger, deeper neural networks and performing homomorphic inference on them. And more importantly, Heon and Seal are currently the two state-of-the-art schemes, but there could be more schemes in the future. It should be very easy to adopt to these new schemes by changing the compiler, so it makes it easy to port. And we did one such porting because Seal was developed while we were doing this, so it was in parallel. And in the future, there are many different things that we could explore. So one example, just an example. So right now, as I said, ReLUs, where we are approximating using polynomial activations, and this is done manually right now. So if we can automate that, that would definitely increase the adoption of this technology. And finally, right now, this is just only for the neural network inference. We would like to generalize this to other application domains as well.
Okay, so let's thank Roshan.
We have some time for questions. I have some questions.
Can you tell us something more about the specific FHE, for example, results?
Yeah.
Depend on the specific model of FHE, for example, some bell pairing or some whatever it is you're using. Can you tell us something about the dependency of the results on the lower level cryptographic primitives?
So this is very specific to the cryptographic primitives that are.
What exactly is it? What is cryptography?
Not the cryptographic expert in terms of the number of instructions supported. So for example, so the way we select encryption parameters is dependent on how rescale is actually supported in the encryption scheme. So Heon and Seal do two different ways of rescaling.
This encryption is actually symmetric encryption.
No, it is not symmetric. There's a public-private key. Yeah.
This is a well pairing from this one. Okay.
So this is
okay.
So it's not symmetric encryption. So it's public-private cryptography. So actually all the FHE schemes that I know of.
No, I understand. That's why I want exactly what exactly it is. Because here many people might assume that encryption means symmetric encryption.
Oh, okay. Yeah. It's not symmetric encryption. That is true. And regarding what they depend on, I mean, again, I'm not a cryptographic expert, but what I do know is all the FHE schemes. I mean, there are different FHE schemes. So there's also a binary FHE scheme called TFHE and so on. So all of these depend on learning with errors problem. So their security guarantees are based on that, and that basically provide. That's why the security standard, actually the Q&N table, is quite. It's common for all these FHE schemes because they rely on the same mathematical hardness properties. The security guarantees are similar for different schemes.
Right. Yeah, so if you look at the compiler problem here, so we're doing both.
I mean, algorithmic transformations as well as semantic determinants. The first thing is you are going to replace the max pooling value with other things that will work with encryption. And so, if you don't want the program, so all of this has to be transferred to the program. If I have a TensorFlow model, I'll take this graph and then I'll take this ops and replace, and then the programmer says use FHE. Some of these things will get replaced, and then there is things like quantization and precision involved, and then all these other optimizations that you're doing. So ideally, you would need some IR infrastructure. That you need to know that these nodes are. You need that high-level information that this is max pooling, and so you can transfer to replace, and then you can perform all the other transformations. And is your goal?
One point before you ask the question. So we are not doing the max pooling to average pooling automatically. That's the point, right? That's future work.
I see.
Yeah.
But in the future, you want the programmer to just use the same TensorFlow or
Exactly,
whatever model
yeah.
and transparently they say, okay, use FHE, and the whole underlying software stack will replace things to actually. That's because do you need any other input from the programmer is the question.
Excellent. So we do need. So there are two currently. So if you ask what are the limitations of this work, so the reason we are not able to take say TensorFlow or Onyx directly out of the box as you said and run it is there are two different things. One is some of the operations are not supported by the FLG schemes. It could be ReLUs, it could be Max, things like that. So those are currently replaced by. I mean, it's not a cryptographic expert. It's someone like me. We basically change the operations, change some parameters, try to tune it to get the same accuracy and so on. That is one thing.
But can that be automated?
It can. We have some work, but we have some promising results, but there's nothing concrete yet.
Because the user probably can't do it. Himself.
Yeah, you would want that to be automated. That's true. So the second thing, I mean, this is you want that to be automated, but there is a notion of approximation involved. So there is a trade-off between getting precisely the same results versus the cost of an operation. So for example, I can replace ReLU with a polynomial activation in general, but the polynomial, the degree of the polynomial will determine how accurate your prediction of the ReLU is, right? So if I use a degree 10 polynomial, then maybe I can match whatever the ReLU is doing, but degree 10 will increase the cost of your program, right? So there is a trade-off there between cost and the accuracy that you get. So that is approximation. So we need some notion of that. So we need some notion for the user to say, oh, I want to tune approximation this way. This is the guarantee that I want, or things like that. So we want approximation semantics to be embedded into the input language itself, in the TensorFlow language. So the second thing here, which I did not get into in this talk, we do get into in the paper, is that for each of the inputs, so I showed you some scaling factors, right? So I have a real number, I need to represent it as a fixed point number. That is currently being done by the programmer, and that's not there in the compiler. So how do you choose these scaling factors? You need to choose them such that your program is accurate enough. So if you choose a large enough scaling factor, your results will be roughly the same. If you choose a small enough one, then your results will be slightly less accurate. Again, there we need notion of approximation semantics in the programming language itself to trade it off.
Yeah, so I think that the programming model in TensorFlow they support or they would support like this
Quantization, exactly.
So that you will get.
Yeah.
So does Himalaya have any of this?
So
Support for
Yes, it has support for quantized types.
Yeah.
So it's not automatic approximation, but you can do it.
You have limitations.
Yes, yeah, the type system has.
So, and the other thing is scaling factor is not exactly equivalent to the quantized type, but I mean, you can map it. So, what I mean by scaling factors here is the cryptographic scaling factors. Scaling factors are actually 2 power 30, 2 power 40, and so on. It represents in the cryptographic thing, but you can have types to denote that. Instead of the quantized type, you would have something like a cryptographic quantized type.
So after the encryption, what does the addition and multiplication of data become? Is it the addition and multiplication of two polynomials?
No, it's some operation on the polynomial, and that's the cryptographic thing. It's some operation on the polynomial. So given two polynomials, you do certain kind of operation on it, and that operation will be equivalent to actually adding those two vectors or multiplying those two vectors. But what they are, I mean, so what they are is not really relevant from the compiler at this perspective. It's only relevant in terms of what is the complexity of that operation. But what we could also do is we could implement those libraries more efficiently. So there's Yarn, there is Seal, right? So instead of using CPU, we can implement them on GPU. There it is important to know exactly how those operations are being done. What we want is to be able to do polynomial arithmetic efficiently on the hardware. And these coefficients in these polynomials are very high. So the Heon scheme actually uses NTT, which to represent those large numbers, they're very, very large numbers. So what Seal does is it changes the cryptographic thing so that you can use normal size numbers, 64-bit numbers. But to do that, they change the semantics of Seal and so on. They use what is known as RNS. So they're given a number, they represent it as 10 different number in 10 different, it's Chinese remainder thing. So they divide it into, again, it increases the complexity if you have to do that. And to actually implement these operations, you need to get into such details.
So when you replace these exponential operations with polynomial operations, do you retrain the model or?
Yeah, we retrain. Right now, yes. That's another factor. So even if you have to do it automatically, can you do it actually without retraining? Right now, that's what we are shooting for in our current work. Without retraining, given the current weights, can we actually do it? And how approximate can you actually get? How accurate can you get without retraining? If you do retraining, maybe you can do slightly more accurate.
So, are some operations impossible to do it in the with R's you cannot do hand, right? So you have sort of basic primitive operations, but you want to do something else, and no amount of juggling will do this.
Yeah.
At least in the case of logic, you know that some chef or something is that just complete.
Yeah.
Right? In this particular physical situations, are there functions which cannot be quote, realized with that's what you have? Is it possible or is it not?
Yes, I mean, with integer or fixed point arithmetic, definitely yes. I mean, there are functions which, even to approximate, it might not be feasible to approximate. Okay, when I say feasible, you would need a very high degree polynomial to approximate. But as I said, there's another FHE scheme is TFHE. So it does bitwise arithmetic. And since it's supposed bitwise, I mean, logical OR and AND, conceptually it can handle everything. But the cost will change. So what it actually does to do that is, I mean, it does. What I didn't get here into this is there's a depth of the circuit, right? So if you want to actually handle, say for example, what if you want to do training on this, right? You want to train by preserving truth. Training is arbitrary depth. You don't know the depth. So what you can do is you can generate Q and N for a particular depth, and then you can do an operation which actually decrypts and encrypts in the encrypted data itself. So it's like it gains you back the Q and N. Right? So that operation is very expensive to do. It's very expensive to do. TFHE actually does that operation for every bitwise operation, and it does it in a very cheap way compared to this operation on integer thing, but it's still expensive. So you can handle arbitrary depth thing, you can handle arbitrary computation and so on, but the cost might change. At least for neural network inference, that might not be the best fit, but in general, you can think of that as another FHE scheme, which might be better for say something like you want to do implement an encrypted database and you just want to do select operation. Maybe TFHE is better. I don't know.
Okay. Any other questions? Okay, so let's thank Roshan again. And